What's up, guys, and welcome to Great Force Solves LeetCode. There we go, we have a name. This is the first time I've done this, but for a good reason, because we have a great question ahead of us. This question has plagued me for like a very long time. I got asked it at my third round interview for TikTok, and despite crushing the first two rounds, this one was too much for me. But I think it's a great question, and it combines a lot of different data structures that are used in these technical interviews, and there's a lot to learn from this question. So let's approach this and make sure we really understand what we're trying to do. So this question is asking to design a data structure that is a cache and then follows the least recently used replacement policy. So what that means is it wants to store key value pairs inside here, but it has an actual maximum capacity here. Otherwise, a dictionary would just solve this question. It has this capacity because it's mimicking like an actual cache inside your computer, and those have a maximum capacity that they can hold. And the catch here is that when your cache has reached the capacity, it should kick out the least recently used item. And what that means is, so we have two methods associated with this cache. We have a get and a put. So the put will take a key value and put it inside the cache, and a get will look inside the cache and see if there's a value associated with that key. And what least recently used means is we need to maintain some sort of ordering inside the cache, and when you put or get anything, that becomes the most recently used item. And then when you reach the capacity, you look at the end of the list at the least recently used item and you kick that out of the cache. So the way I approached this in the interview, because I really had no idea what was going on, I eventually arrived at like a half-working solution. What I thought is, obviously you need some sort of dictionary here, right? So you can store in like key 1 value 1, key 2 value 2, key 3 value 3, whatever. And then you also have like some sort of ordering list where I wanted to put in like, okay, key 1 went first, key 2 went second, key 3 went third, whatever. And the part that I struggled with, that I couldn't figure out on the fly, is there's a big issue with this approach. So let's say we have this list here, and this end is the least recently used end, and this end is the most recently used end, because that's the one we added last. Let's say we have like a put K1, put K2, put K3, but then we have a get K2. What this cache should do is get rid of K2 and append it again here. But there's a big catch with this, which is actually the hardest part of this problem. The way I did this in the interview is the brute force method, which I would just search through left to right of my list, starting at the LRU end and getting to the MRU end, and see like, oh, is this K2? No. Is this K2? Yes. So take it off and then append it here. But there's a problem, that's O of n complexity, which for a cache is actually pretty bad. So the question actually asks for constant time complexity, which is much faster. What this means is for every single get or put, if something like this comes up, if you're doing it with a list, you have to search through every item at the worst case, which is O of n, whereas the question wants you to be able to just know where this is. With no searching, just boom, gone, and then append it again. So that's the solution I came up with first, and after some further research on this, there's a much better way to do this. I should have known, now that I'm thinking about it, when a programming challenge asks for constant time complexity, there's a very short list of ways to actually achieve that. You can either use a hashed structure like this, which I did here, but not in my ordering list. That's not a hash structure. So you can achieve O of 1 by using a dictionary, or by using a set, or by using a stack, but a stack that maintains some sort of ordering, but that isn't really applicable to this question. And the last thing, which I didn't think about for some reason, a linked list. So the correct way to approach this is, let's say we have the same scenario here. You create a linked list where you start at this node, which is going to be key 1, value 1, which then points to this node, which is key 2, value 2, which points to this node, which is key 3, value 3, and so on. And this is the LRU end, and this is the MRU end. And to make this easier, with a lot of linked lists, we do something where we add like a dummy node, so something that just doesn't really exist, but it'll just tell you which end is the LRU end and which end is the MRU end. And you might think, there's something at least I thought when I read that you were supposed to, this is actually a linked list question after the interview, when I looked it up real quick, and I was like, how does that work? Because regardless, if you get this get K2 thing, my thought was, well, how do you know which node is K2? Like, I would, again, have to start here and just traverse the list and be like, oh, I found it here, pop it off, and then append it to the end. But there's actually a very smart way to approach this, where in the cache itself, instead of this just being key 1 value 1 and key 2 value 2, whatever, instead of these being 2 integers, the keys are the keys of the cache, but the values are actually a pointer to the node inside of the ordering linked list. We can set this up so each key points to the one that it's at, and then when you go to get K2, you can access K2 in constant time, traverse this in constant time, and then just eliminate these 2 links in constant time. And that's how you're supposed to actually approach this problem. And because you need to like pop off the LRU and the MRU, there's kind of like complicated, I forget the specifics, but we'll probably run into it in the code. This needs to be a doubly linked list. I forget right now why, but let's dive into the code and I think it'll become clear. So we need to initialize a couple of things. We want a capacity, so we can set capacity equal to that. We want an ordering, which is a linked list, but I don't think we should put this right in here, so let's set up another class over here. I like to call it list node, and this can also have its own constructor, and it can have the key and the value associated. So self.key is key, self.val is value, and it's going to have a previous and a next node. I'll set these equal to none because I think we can assign these on the fly. And then going back to this cache, so we need a capacity for sure. And looking at this, we need the LRU and the MRU end. So I think we need to set up like a head and a tail node that are these dummy nodes. So we know when we need to pop off the LRU item, we just pop off whatever's at the head, and when we need an MRU item, we pop off at the tail. I think that's why actually we need this doubly linked structure. Still not entirely sure that though. So we definitely need a head, and we need a tail, and I think we set these 2 dummy list nodes here that just have 0. But to initially set the structure up, I think we need to connect these together, because right now we'll just have the way we set this up is we have these two dummies, and they're not pointing anywhere because I set these to none, and we kind of want them to at first point to each other, so then we can update these when another node comes in. When I'm doing this, I don't know exactly what I'm doing. I did solve this question a couple days ago because I wanted to finally get to the bottom of it, but I'm trying to come up with this on the fly a little bit, so it might not be perfect. So I think we want self.head.next to be self.tail, and then self.tail.previous to be self.head. But I could be wrong there. I'm not too sure right now. And then we can approach these methods, the get and the put method. Starting with the put, I don't think this should be. Oh, we're missing the most important part, the actual cache. We need something to put the key values in. So we can go. There's a couple cases, but we can start with the most obvious one, which is you have the cache at the key and you set it to the value. But there's a couple cases with the put. The cache can have the key already, and in that case you want to update it. It can not have it, and I think that's it. And with the get method, if it has it, then you want to return it, otherwise you don't want it. And I think the way to check this is you have to go if key in self.cache. You can't try and index it and go, I used to try and do this, if self.cache key, but that gets mad at you because if it's not in there, then this if statement throws an error in Python. So you need to like check if the key is in the structure itself. And if it is, we need to update the ordering, and then we need to return the value. So we'll grab the value like that and return it. And then if it's not in the cache, then we can just return -1. And we'll get back to this update ordering over here. So going back to the put method, let me think here. So if it's in there, so I think we need to do like a similar check. If key is in the cache, we can grab it. And then we need to update ordering, and then we need to actually do something. So if it's in the cache, we just have to update it. So we can go cur.val equals value. And actually here we don't return cur because cur is a pointer to the list node. We actually need to return cur.value. And then if this is saying if it's in the cache, then we just update it. Otherwise we need to add it, but before we add it, we need to check whether the capacity has been reached. So we go if the length of the cache is greater than the capacity. Here is when we kick off the least recently used value, and then I think that's it. Actually, I think we can just kick off the least recently used value. And if it passes both of these, so if it's not in the cache, we're gonna return here if it is in the cache, so we don't actually trigger the rest of this. So if it's not in the cache and it's within the capacity, then we add it. So self.cache at the key, it's not a value, we actually need to create a list node here with the key and the value. And not only do we have to do that, we need to update the next and the previous pointers. But I think there's a better way to do that. So if you've noticed, I have a bunch of sections in here that are telling me to do something, And the best way to do that is to, well, not to just to do that, but to abstract it away, is we need remove and insert helper functions, which I think will also help with this problem over here that I'm not entirely sure about right now. So we have remove and we have insert, because if we look at this and we have this get K2 here that we want to satisfy, we need to access this K2 here, traverse this over here, and then remove this node, and then append it. And that, since we have these dummy nodes, should work in every case. There shouldn't be any edge cases, because with both dummy head and tail nodes, every insertion is between two nodes. There's never like only one node where we need to check like an edge case, like, oh, this is the new tail. That doesn't happen because we have the two dummy nodes. So let's create these methods. So we're gonna remove self, we're gonna move, or it's a method, so it needs this, and we're sending in a node. And this node has both a previous and a next pointer, so we can actually remove it in place in the middle of the list. That's why we needed the previous, because otherwise you can't remove this because you have no way to access the next pointer of the previous node, and so the link would be broken. Because if you just remove this without being able to access this guy over here, this arrow would point nowhere, and then the link of the list would be broken. Let me just clear this up a little bit. So, taking a look at this remove here, we need to update mainly just these two and these two links, because we want to create something where we have a link around and around, like that. So to do that, I think we have to do node.previous.next equals, well, we want node.next, so we actually need to store, it, I think. Next is, or let's just call it temp, is node.next. Let me bring this over here so I can really think about this. So boom, bam, boom, boom. So what we're trying to do is node previous next is actually the old node next, which I don't think we need to store anything for that. We can just do this. So then that would do previous next. That would get rid of this, and that would create that connection there. And we want to do node.next.previous, so we traverse that way, is node.previous. So now node.next.previous, this gets destroyed, and this goes like that. And that works because now this thing is not attached to the list and it points to nowhere, so the Python garbage collector will take care of the rest for us. Cool. And now insert a node is a similar deal. What we want to do, let me set up this scenario again. It's nice to have the dummy nodes because every single insert and remove is between two nodes. I don't have to deal with any edge cases. Let's say I wanted to insert a node here. I guess we don't, wait. Let's just do this. So we have, it's a bad arrow. We have something like that. We want to insert something here. So node, Actually, I don't think it's the scenario we're doing. Because when we're removing, we are removing at an arbitrary point inside the linked list, but when we're inserting, it's not actually an insert, it's an append. Because we just want to append if we do anything, we want to append it in this spot, in like the most recently used side of the list. There's no actual like purpose of inserting in like the middle of the list. Because that's just not how the replacement policy works. No, yeah, this is incorrect. What we want to do is we have this tail, and we have a node that's already connected, and we want to put it here. So we can do node.next is self.tail. Self.tail.previous is node. So node next is self.tail. This gets deleted and goes here. But before we delete it, I think this is where we need the temp. Self.tail.previous is now stored in temp. So then we can do node.previous is this temp that we got, and temp.next is the node. Yeah, that should work. Because we hold this value here initially. Then we set up a new node. And we go next is the tail. And then we go tails previous is that new node. And then we go nodes previous is the temp value we held. And then the temp values next now is that node. So that actually gets rid of this too. Cool. So now that we have these helper functions, I think we can attack this ordering stuff. So the key's in the cache, we get the node, we remove the node, and then we insert the node, and then we return its value. And then, okay, here in the put, it's in the cache, we remove the node, we insert the node, and then we update its value, and we return. And then here, if we've reached capacity, we want to remove the least recently used item, which is this head next node. This is the one we want to kick off. And since again we have a dummy node, it's just the same scenario that we wrote that method for, so that will just work great for us. And then finally, if it's not in the cache and we're not at capacity, we can just set the key equal to a node as the key in the value, and we want to insert it at the most recently used spot. So we want to insert at self.tail.previous. And this should work. Let's submit it and see. No. What's wrong with this? Num type has no attribute next. Where? And get? Wait. Line 32. Okay. Let me just run through this example. So, capacity of 2, we put 1, 1, 2, 2. We try and get 1. And it doesn't like this connection here. Let me get some more space here for this example. So capacity of 2, dummy node, 1 1 2 2. Just form these connections. Unless I inserted it incorrectly, which I don't know, because we have this node. No, wait, yeah, no, I did this wrong. No, we're not inserting the one previously in the tail, we're inserting the thing we just made. Yeah, because the insert function just inserts at the most recently spot regardless. So you need to insert this node, and I think that's what or this might actually be correct, because we do want to actually remove the node at head next. But I think, let me try this. Okay. Oh, this was much better. No more error. And now it's saying put, get. So when we went 1 1, 2 2 is in, 1 got updated, and 2, when 3 got put on, 2 never got kicked off. Let me see here. So this is still useful. 1 and 2 are good, and then 1 gets accessed again, so these actually switch spots. And then 3 gets put on, so 2 2 should get kicked off, and then 3 should get put in here, whatever. But that's not happening. But we don't have an error to really work with here, so let me see. If this is in here, we get the value, we remove it, we reinsert it, we update its value. Has reached the capacity, so the length is currently the capacity, and you want to put in a new value. This is when you remove the least recently used node, which should be self.head.next. And then it's not in there, or if the capacity, well, either way the capacity is satisfied at this moment, so then we can insert at the key a new node that we create with the key value, and then when we insert it, we do update both its next and its previous values. Okay. So what's not happening here? I'm a little confused. Remove should work because the previous next just becomes the current next, and then the next previous becomes the current previous, and the insert, we get what was the previously most recently used item, and we set this new node's next to the tail. The tail's previous to the node. The node's previous to the old recently used, and this one's to the node. And here, if it's in the cache, we want to return that, and if it's not in the cache, we want to return this. So It's in the cache when it shouldn't be in the cache. Does this ever happen? Maybe it's not supposed to be equal to, so it happens once. The problem with using a linked list is you can't really print out the whole list nicely. Oh wait, no, it happens again here. Where we return 1 when we shouldn't be returning 1. But this thing executes. It executes once. Let's see what it's kicking off. So it kicks off 2-2. I think that's what it was supposed to kick off. It throws on 1-1, throws on 2-2, reaccesses 1, and then when 3-3 goes on, it kicks off 2-2. When 3-3 goes on, it kicks off 2-2. And then when you try and get to, oh wait, no, it kicks off the value from the ordering linked list, but it never actually deletes it from the cache. Boom. This is gonna be it. What I did was, so we have this cache structure where we have 1-1, 2-2, and then when we go to do this process of actually kicking off 2-2, we don't touch anything in the cache, and then we just throw 3-3 on, because there's no actually inherent ordering built into the cache itself. And I just set this to be equal, which would work if we actually updated this, but isn't working, because we're not actually doing anything. So then when it looks into the cache here, it actually sees the 2 value. So we need to not, there's like a, yeah, we need to delete this. That's gotta be it. Okay, it was not. Am I just doing it in the wrong spot? Delete. Line 47 doesn't like this. Why doesn't it like this? No, wait, yeah, because I'm jumping to conclusions here. We're not deleting. We remove this from the linked list, but we need to delete. We have the key here. Delete self.cache at the key. Saying key error. It's trying to enter a value at a key. Oh, and it doesn't exist yet. We want to delete this value's key, not just the normal key. It might be simpler to just actually extract this or that. So then you can just remove this, and this makes a bit more sense. This should be it. But I'm not 100%. Oh, let's go. Yeah, that was it. Yeah, because I was indexing the key that they wanted to put in the first place, when really I want to delete the LRU key. which is, of course, this value right here. Well, because this isn't actually a value, it's a pointer here, so we removed it from the ordering linked list, but we also want to remove it from here, which requires you to get the key from the head and then use it to delete it in the cache. Let's see if it passes all the edge cases. It should, because we use the dummy nodes and we're careful about the inserts. Boom! Let's go. Pretty good runtime. Solid memory. This stuff doesn't matter. The complexity is constant, and that's the only thing that actually matters. So, we did it. This was a tough one. This is a really... I'm surprised I got it without having to look anything up at all. And it's a great question. It tests a lot of stuff. I don't know how anyone would come up with this on the spot in an interview in 45 minutes with an interviewer questioning every move without having seen, studied, and solved this problem before. But whatever, I don't get to choose the game I play, I just play it, and eventually I'll get through. If you got this far, thank you for watching. Let me know if you want me to solve any other LeetCodes, because I will do them by request. And yeah, see you till next time. I'm gonna do this fairly frequently until I actually land an internship, because I've gotten through many processes pretty far and can just never close it out. So this is the practice I actually need to do. See you next time.